presentation, but again, this is a bit embarrassing as Dan is the person who arranged for this talk, but anyway, it's really a pleasure to be here and to be able to give this talk here today. So this is ongoing work. I do hope we'll manage to submit the manuscript in a few days, but we have been working on this for quite some time, as I said, in collaboration with Dan. It's a pretty old problem that we are tackling here. Actually, what I'm going to talk about is how to estimate the parameters of a state space model, something that people have been looking at for many, many years, but apparently it's not so easy to settle this problem. So I have quite a lot of slides for today. I'm not sure that I will be able to show you everything, but this is the general structure of it. Maybe I will skip some parts, probably here in the analysis, depending on time. But let's see how it goes. So I will start with a brief introduction. I will explain what my model is. I will formally state the problem too. I will describe the algorithms. I will take some time for this. Then I will try to give you an idea of the kind of analytical results that we have managed to obtain. I will put the emphasis on the assumptions that are needed and what you are able to get rather than the analysis itself. And then we'll show you some numerical results for a simple example using a Lorentz model. So, as I said just 2 minutes ago, we're trying to build a particle filter that yields a posterior probability distribution of the model parameters for some dynamic system. So we know that particle filters are very good at tracking dynamic variables for such systems, but we also know that if there are any parameters that we don't know, then we are usually in trouble to handle them. So we want to do several things, actually. We want to address the problems of tracking the time-varying state variables of our dynamic model. We want to estimate any fixed parameters that there may be in this model. We want to do the two things at the same time, and we want to do them online. So we don't want to have to reprocess iteratively a whole bunch of observations that keep coming to us, especially because this bunch of observations doesn't necessarily have a finite length. I mean, we might be getting observations forever. And we want to do all of this for a pretty general stochastic state space system. So this is a rather old and tough question. People have been working on this for years. Probably all of you have taken a look at this at some point. And, but apparently it's not completely settled yet. There are solutions, I will discuss them a little bit later. But apparently it's not completely settled.
Sorry, when you say online, you have an algorithm that has a constant CPU cost?
Yes.
Per time, I mean.
Exactly. What I want to do is to simply update my solution from the previous time instant without need to reprocess everything from time zero. So my model is this one, which is pretty standard. It's just a state space model with a Markov signal process. So xt is the state, the dynamic variables. I'm using tau for the transition kernel, so this tau, which I admit to be inhomogeneous, so to depend on time, determines the dynamics of my signal process, of the state of my system. Yt are the observations that are produced by the system. And I'm making the usual assumptions. So tau is Markov. I assume that xt depends only on xt minus 1. And I'm assuming that my observations are conditionally independent. So given xt, I have the density function g that describes my observation yt. Now, the tough bit is that both tau, the transition kernel, and g are indexed by some other parameters, by some theta. And then I have some priors. I'm imposing a prior mu on my parameter and a prior tau on my state. I'm assuming that these parameters, these priors, are independent. So tau naught doesn't depend on theta, mu naught doesn't depend on x. The state, the observations, the parameters can be vector valued, arbitrary dimension. And of course, we can build a probability space so that at time t, I have this capital P sub t that describes the joint probability for my sequence of states, my sequence of observations, and my parameter.
Can I ask something? Since this is more informal, why is it such a big deal that the tau zero doesn't include it?
It isn't. I really was a bit lazy.
No, it's fine. I was just wondering if there's some strange reason why this is so important.
I don't think so. You should be able to work out everything again, but it would be a bit even longer than it is. I don't think there's any problem with that. I wouldn't be able to guarantee that anyway. So again, this is our model, just to keep an eye on it. And what is interesting in this model? Well, the usual things. So given the parameters, we may be interested in the optimal filters. So this phi is going to be the filter, so the posterior distribution for the state, given the observations and the parameter. We may be interested in carrying out predictions. So this psi is the usual one-step ahead predictive measure, given the observations up to time minus up to t minus 1, and the parameter theta. And today we are particularly interested in the posterior for the parameter. So this is mu t, is the density, well, probability distribution of my parameter given the observations up to time t. We'll also say something about the joint posterior measure for the states and the parameter. And our goal is, well, basically, we want an algorithm that produces everything at some point. So I will show an algorithm that can potentially track mu t, psi t, phi t, and pi t. So the posterior for the states, posterior for the parameter, the joint posterior for both of them, under some assumptions, of course. I will want to do it recursively and online using some Monte Carlo algorithm, as I said in the beginning. Now, the problem is quite straightforward. I mean, it's quite natural. So people have been working on this for many years and proposing all kinds of solutions for this. So maybe I want to say the oldest one, but one very well-known algorithm is this from Jing Li and Mike West from 2001. I think they published it earlier in some other journals, where they essentially build a kernel approximation for the PDF of the parameters given the observations, and then incorporate this into an auxiliary particle filtering scheme to produce samples from the parameters and the states. However, anyone who has played a little bit with this algorithm can see that normally it only works in very simple cases with just 1-2 parameters at most, and you can even find some cases that simple, but the algorithm doesn't really work. It's kind of not robust or unstable with respect to the parameters. If your state space model has some structure, you can of course use it. So if you're lucky and you may be able to integrate out the parameters, and this is what we often do with all these mixed Kalman filters, supervised particle filters. And then there is like an intermediate step where your algorithm has some structure but not enough to integrate out your parameters. In some cases, you can actually compute sufficient statistics that describe mu t. And in that case, although you cannot handle the parameters analytically, you are able to draw from some posterior distributions, and the Monte Carlo approximation becomes much more efficient. But this is not something that you can do actually with every single system. Since designing Bayesian methods, so some methods to approximate the posterior distributions, seem so difficult, many people looked at different alternatives. One of the most popular is the recursive maximal output algorithm. Actually, we had Tadic last week talking about it. And the basic idea is that you have essentially a stochastic approximation algorithm or some kind of gradient algorithm to maximize the likelihood of the parameter. And this is coupled with a particle filter for the states. So you use a particle filter to approximate the posterior for the dynamic variables given the parameter. You use this information in the algorithm, in the maximum likelihood estimator, to keep adapting your estimate of the parameter. But what you get is a point estimate in this case. So you don't obtain a distribution in general for the parameters. There are various versions of these algorithms. They seem to be, in practice, quite useful, and we also have some analytical results about them. As I said, Rich was talking about this last Friday. Then lately, we have a nice collection of batch methods that solve the problem. We have seen a lot of particle MCMC and exact approximations last week. We didn't see much about sequential Monte Carlo square. You guys should have talked about it. But you can also design a sequential Monte Carlo algorithm that solves the problem. But this sequential Monte Carlo algorithm is not strictly recursive, because occasionally you may have to take the whole sequence of observations and run particle filters from scratch. And you can also design some population Monte Carlo algorithms to address this problem. So next I'm going to talk about the algorithm, and the structure of the algorithm is basically the structure of the sequential Monte Carlo square. But we will try to figure out how to make it strictly recursive. So we need to assume the system to make the algorithm strictly recursive and still provide guarantees that it will work. So we are going to try to track these four measures: the optimal filter given the parameter, predictive measures given the parameter, the posterior for the parameter, and the joint posterior. And I want to do it using a particle filter. Not only that, I like simple things, so I would like to do it with something that resembles the bootstrap filter as much as possible. So I want to have something that behaves essentially like a bootstrap filter, but can work for the parameters.
Sorry?
Yeah.
You said that you want to track the filter, but there's a conditioning on theta. So
Well,
I wonder what you mean there.
what I mean is that I'm going to generate samples in the space of the parameters, and for each one of these samples in the space of the parameters, I will actually obtain as a
conditional
result. Yeah, exactly. Conditional point values in the parameter space. I'm not saying that I'm going to get anything original than that. So I'm going to go through the something maybe it's not needed, which is the conditional particle filter. The only thing I'm saying in this slide is that I will use as a basic building block a bootstrap filter. So if I fix my parameter, say my parameter is theta I, then I can simply build a standard bootstrap filter for this. I just draw from my transition kernels, compute weights according to the likelihoods, and resample. Now, what this conditional particle filter is giving me is a cloud of particles in the state space associated to this particular point in the parameter space. So if I fix a set of parameters, a point in the parameter space, I get a cloud of particles representing the optimal filter for approximating the optimal filter for that particular point in the parameter space, so for that particular choice of my parameters. What can I do with that? Well, what I can do are the usual random measures approximating the conditional filter, the conditional predictive measure, and we know that these conditional measures actually converge. We can prove convergence for these ones, again, condition on the parameters. When we say that they converge, when I say that they converge in this talk, what I mean is that we can approximate intervals with respect to these measures. So I'm using this shorthand for integrals. So this is the integral of the function f with respect to a measure alpha. When I say that my conditional particle filter is converging, I mean that this integral, for instance, with respect to the predictive measure, can be approximated in this way. So the integral of the function with respect to the discrete random measure, which gives me simply this average, the use of them. Now, it's clear how to do the bootstrap filter. It has been clear for many years. How can I do something similar in the space of my parameters? Well, I'm basically going to mimic the steps of the bootstrap filter, and I can write up something like this. So I can draw samples in the parameter space at time 0 from my prior. I made it independent of the states, so this is straightforward. And then at time time t minus 1, assume that you have this cloud of samples in the parameter space, so you have this approximation for the posterior at time t minus 1. The bootstrap filter, you would go and draw from the transition kernel. What I'm doing here is, oops, this is that. Is that I don't have transition kernel, so I'm going to invent another kernel, anything basically, that I use to jitter my samples in the parameter space a little bit. So I will impose conditions on that, but for the moment it's just some kernel. It doesn't have to be an MCMC kernel, it doesn't have to be anything that leaves some distribution invariant, just something that introduces some noise. Eventually, I will want to control that noise in a way. So what I managed to do at this step is to jitter, so to shake my cloud of points in parameter space a little bit. I may be introducing some bias, maybe I might even be screwing it up completely, but we will look for conditions to avoid that later. Once I have shaken my samples a little bit, I compute weights. Now, the actual weight I would like to compute would be the marginal likelihood for that point in the parameter space. This would be this integral, which is the integral of the likelihood function for my, or the conditional density of my observations for that point in the parameter space, for that parameter, with respect to the predictive measures of the states given that parameter. Of course, we cannot obtain that exactly, so I've talked ahead of myself. So we cannot compute this exactly, but we know how to approximate it. Actually, this is same as the idea as all these talks on exact approximation that we had last week. So this means that the algorithm as it stands is not practical, but if we simply plug an approximation for the weight here, then this is practical. This is something we can implement. And the natural way to approximate these weights, of course, is using a particle filter conditional on this parameter value. Now, this algorithm written like this is almost exactly the sequential Monte Carlo square algorithm. Only that the way sequential Monte Carlo square, if I'm not making any mistake, tell me otherwise, you actually choose this kernel to leave the distribution of your parameters invariant.
We don't do it every time.
Exactly, yeah, true. That's something I didn't mention in the last slide. I'm also writing here a resampling step at every time step. This is not really needed, not really desirable in practice. You don't want to resample every time, but I'm doing that for simplicity. I'm not really. We have not really looked at implications of adaptive resampling in this algorithm. Okay. So this algorithm is practical because you can implement it. Whether it is recursive is questionable. It depends on how you manage to compute this thing here, this weight, and whether it will converge is something that may look unclear. It's something you have to look at, you have to prove. Now, the obvious way to compute the weight is to take your theta t, so your point in the parameter space, plug it into your particle filter, and run your particle filter from scratch, from time zero. The problem is that then the computation is not recursive. Every time you need to do that, either where it is at every time step or only when you resample or when you do something, it means that maybe at time 1 million you need to go back to time zero and run everything from the very beginning. So this is what we wanted to avoid. But actually the way to avoid it is pretty simple. A different question is whether the thing is going to work later, but it's pretty simple. As we said, what the particle filter condition on the parameter is actually doing, what it is producing, is a cloud of points in the state space, which is linked to this parameter. So why don't you take that cloud of points in the state space and simply assign it to the new value of the parameter? So what you're doing is that you are taking this parameter theta at time t minus 1, I, so the ith sample, and you are using a jittering kernel to move from here to this other parameter, theta t bar I. What I'm saying is that if you control the way in which you move from here to here so that you don't introduce too much jittering, then it's fine to assign the old cloud of particles in the state space that corresponded to the old parameter. It's fine to assign it to the new parameter. This is all that I'm saying. Once you do that, you can propagate the cloud of points in the state space using the transition kernel with the new parameter, and you can compute weights for the particles in the state space using your model, so the density of the observations indexed by the new parameter. And then you resample. I'm assuming resampling at every time step, as I said. I'm not worried about that resampling here. In this way, we obtain approximations for psi, the predictive measure in the state space, and for the optimal filter, all of them conditional on the parameter in a purely recursive manner. So we never need to go back to time zero and recompute anything. Now the question, of course, is, does this make sense? Does it work? Well, before trying to convince you that it will work, this is a picture of the algorithm. Actually, it's not very different from other things that are around there. It's like it's nested particle filter, so you have two levels of filters. And what you do is that graphically you take your sample in the parameter space, you jitter it, so you change it a little bit, obtain the theta with the bar, then you compute weights. The computation of the weights means that you have a full filter, particle filter, associated to the parameter, but you only need to take update the steps. So computationally this looks, or from this point of view, computationally from this point of view, this may look very similar to the use of localized particle filters to which we are used to. And again, it's only updated states that are taken here, only updates. You do this for every particle, you resample, obtain a new cloud of points in the parameter space, and you keep going.
If you take one particle filter for every theta, this is exactly the question.
You take one particle filter for everything.
One particle, sorry. Yeah, that's what I mean. System of one.
Good point. Good point, but I'm not sure it's exactly like that.
I was asking more than stating, but maybe stating with some degree of belief in the statement.
I mean, it is true. If you take just one particle at the state space, for example, in parameter space, you would get something at least looking like Leon West. But he's doing more things. I mean, he's still building this approximation of the PDF for the parameters, PDF for the parameters.
Yeah, but that's basically the kernel that you're using. So.
Yeah, it reminds me also, I think it's in the Gordon, Salmon and Smith. So basically, it looks like you're incorporating the static parameter in your state and you're Raoult-Blackwellizing what is really the state.
Yes.
Yeah,
Yes, but numerically, but you do it numerically. Yeah.
Sorry?
Yeah, but you do it numerically. I mean, what you are. I mean, if we were able to solve for the weights exactly, you would be integrating out the states instead of the parameter. Yeah, that's correct.
I'm not quite sure what these small yellow bars are. Are they a resampling step, or is it just
This
one
one.
particle that goes through? Do you see the small yellow bars?
The small yellow bar. Oh, these are resampling steps. Yeah.
So there is a resampling step on n particles
Yes.
for each value of the parameter.
Yes. Again, this is something you don't really need to do at every time, but we haven't looked at that. Yeah.
Can I ask, so what do you say that the Gordon, Salmon, and Smith do?
Wait, I haven't looked at the paper for a long time, but I think that what they were saying, they were just saying, well, we've got a static parameter, let's pretend that it is part of the state, and we introduce a dynamic to get the ergodicity, and then you've got an approximate model.
Ah, okay, but this is the idea that many other
Yeah, and then you just run it. But here the only thing is if you're using the particle filters for each theta,
it's
it looks like you're
marginal
integrating the true state.
Yes.
So with one particle, you would recover,
Exactly. So
which is related to your remark.
I think I've misunderstood perhaps the crucial part. Could you just go back?
Yeah, sure.
So this bit, step one, right?
Yes.
So this is the important bit. So with the bar on, it's just after you've jittered,
After jittering, yes.
right? So you jitter and you just say, just keep the x's anyway.
Yeah, exactly. I'm saying I have a cloud of particles in the state space from my old parameter. I'm going to jitter the parameter slightly to get a new one. And then what I say is I just keep the same cloud because I'm kind of hoping that my modified state space model with my modified parameter will not behave very differently from the old one.
Well, actually, in principle, you're passing on the previous C filter and the previous estimate of the likelihood because it's like a Markov process. If you look at them together, because you need that previous estimate of the likelihood to use the new incremental likelihood with the new theta to keep going. Because you're
Well, yeah, but I'm resampling at every time step, so
okay. Yeah, but if you didn't,
true. Yes. So yeah, that's what is done, and the question is whether that makes sense, whether or what you have to impose on your system to make sure that works. That makes sense.
And works in what sense? When n goes to infinity, or?
Well, when n goes to infinity, and we also have some results when t goes to infinity.
For n fixed t. Okay, well, okay.
Yeah, we'll get there. We'll get there. Yes, hopefully. So, what I'm doing next is I will talk about the assumptions that I'm imposing on the system. I will do it quite loosely first and try to state the results that we have. And then if you are willing to look at it, and we have time, I can go into the specific, the specific assumptions that we needed in detail. Okay? So, if we just impose some control of jitter invariance, so you basically choose your jittering kernel so that the variance has some upper bound that depends on the number of particles. And it's quite easy to get that. I will show you later, but it's quite easy to get that. And the conditional filters are Lipschitz. And you have some bounds on the likelihood. This bound, well, it's not written here. I should have written this in a better way. This bound has to be uniform on theta, okay? Not on x, not necessarily on x at this point, but uniform on theta. this one is uniform on theta. Then you have, using just a very standard induction argument, you have this kind of results. So you can take a bounded function h in the space of the parameters, and you can approximate intervals of this h with respect to the posterior of the parameters, and find upper bounds and convergence rates for the errors in LP. And this is the same kind of results that you obtain by the same kind of argument with the bootstrap filter. And also with the same assumptions, only that we don't need to impose this thing here. So we need this bounding likelihood, which is uniform in theta. Okay. If you have that, then by the same kind of arguments and do it with some care, of course, you can actually show that you have this kind of convergence rates, and you even have them for the conditional filters that you have for your samples in the parameter space. The problem, of course, is that these constants depend on time, and it's not difficult to show that they actually grow and they can actually explode. So these results make sense when you have a finite time horizon. But you can obtain that. You're just putting everything together and controlling the variance, just the variance of the jittering kernel. You can get that.
What do you mean by control?
Well, let me go ahead a little bit. Maybe we'll come back later. Something like this. This is what that when maybe assume that you are trying to integrate a Lipschitz test function, then you only need this one here. So what I'm saying is that no matter from which parameter theta prime I start, this interval, so the pth order moment, has to be controlled with some rate that depends on n. So you need to have a constant here over n to the power of p over 2. This is what I'm saying. So I'm not trying to suppress the bias, anything. I'm just saying if I want to look at second order moments, I have to control the variance. If I want to look at higher order moments, I have to control the corresponding moment for the jittering kernel. That's what I'm saying. You need something similar for the function, but the test function, you make it to be Lipschitz, then you get this automatically.
Can we suggest? So you want the jittering to be more and more concentrated as you increase the number of particles.
Many points, then you check them less.
Because you try to balance two sources of error, basically.
Yeah. So actually, I'm not sure I can show you specifically with these slides, but there is something nice about it, which is in the paper we actually have like a class of jittering kernels that one can work out very easily, and they have a nice property, which is that if you can you have your set of particles or samples in the parameter space, okay? You can either jitter just a few of them, and then if you just take a few, you can actually make them change quite a lot. Or you can jitter many of them, even all of them, and then you have to shake them less. So you have to introduce less noise. And in both ways, the theorem still holds, so you can still warrant the convergence. So what this is saying is that actually it's not how much you move a single sample, it's how much you move your ensemble, how much you move your cloud of samples in the parameter space.
So, sorry, can I ask a question, because I can't remember the setup exactly. So n is the number of thetas and the number of particles for each particle filter is the same number?
Yes, I'm using the same number to make things a bit simpler and shorter for the analysis.
Yeah.
It doesn't have to be.
Well, they both have to go to infinity.
Yes, and actually the rates would work for the minimum
Yeah.
between the two numbers. I mean, if you have a different number, for one layer and for the other, the rates work, but for the minimum you need to do it.
So of course, I don't know how complicated the math is, but do you really think that it's a good idea to couple your condition on the kernel with n? Because really, in reality, what you want to do is you want to fix your number of particles, and then you want to measure somehow the approximation you're introducing with your jitter. You see what I mean? You don't want to couple them, but I think that what I want is to use the particle filter with a fixed number of particles, and then say, well, you know, I've got a parameter on the jitter, you know, and if I put lots of jitter, my approximation would be bad, and if I make the jitter less, it's going to be better or maybe worse because you're losing elasticity. I don't know how it works. You see what I?
Yeah, I think so. I don't think it's a problem really. I mean,
but it would be more informative, I think. No.
Maybe let's wait for the time uniform thing.
Yeah.
Well, what I would say is that, yeah, in practice, you basically have a constraint in your computational effort. You can afford a certain number of particles. In that case, these results are, at most, they are giving you a kind of hint on how you can choose your the variance, let's say, for these jittering kernels, no more. Since the bound that you have on that variance has the form of a constant over the square root of n, basically. If your n is fixed, then of course you can take any constant and you can make that value whatever you want. So it's just a hint. That's true. So it's not something that you can say tune automatically to optimize the performance online, something that sophisticated. It's not that.
I'm surprised that the jitter does not depend on time, because what you typically observe is that the posterior concentrate at a certain rate. So
Yes.
after the long time, maybe your posterior is almost a Dirac mass, and maybe even jitter should be much smaller than what you used to do.
That's 100% true.
Okay.
Indeed, it would be desirable to do that, but we haven't. The only thing what we have is that as t goes to infinity, actually we have some results to see what happens when the posteriors converge into a delta. What you see is that as time goes to infinity, your posterior exactly goes to that delta. You still have your cloud of points, and the error depends on n. If n goes to infinity, the cloud contracts, the approximation improves, but and also the jittering noise, so to speak, goes to zero. But it's completely true. I mean, it would be good to have that kind of.
But isn't that question the same as the fact that you need to take n as a function of t, really? But that's the uniform thing that maybe we need to do. But you need to take n as a function of t.
I'm not doing that. I'm not. Not really. Not really. What the uniform result is telling you is that if your optimal filter is stable, then it forgets the approximation errors, and it basically behaves like a particle filter for a certain fixed window of time. Yes?
So just a point of clarification about the algorithm again. So for x's, the states, each one of those particle filters is a conditional bootstrap filter conditioned on one jittered sequence of thetas. Is that right?
Yes.
Right. And then, having done that for each jittered sequence of thetas, how do you actually compute the weight for the thetas? What's that procedure?
It's the weight for a particular theta at the time t is actually the integral of the conditional density of the observations.
So you take the Monte Carlo estimate of the marginal likelihood?
Yes.
Okay, right. So it's like a sort of Monte Carlo rare blackwellized filter, as I think you said earlier on. Yeah. Okay.
I mean, it's
with jitter on the parameters.
For the weights, it's the same kind of approximation used in exact approximation algorithm.
Yes. So you have this kind of unbiased property on the jitter.
Yes. We're not using it, however. I mean, we are not using the unbiasedness in the proofs, but yeah. Okay, I think we were actually somewhere. Yes. So you can have this kind of results, but of course the constants depend on time, and that's not so nice. How can you get rid of them? Well, you have to impose stronger assumptions. So again, you have to control the jittering variance. Well, I shouldn't say the variance. You should control the before the moment, as I have just shown you. But that particular assumption is exactly the same one. Okay, this number one is exactly what I have just shown you 2 minutes ago. You need the conditional filters to be Lipschitz continuous. So you need continuity both in the G, so in the conditional density of the observations, and you need continuity in the Markov curve as well. We'll show you the assumptions exactly later. And you need, and this is the interesting part, okay, you need bounds on the likelihoods, on the G's, and the conditional density of the observations. Now, what is different in this bound that we are using compared to previous work is that we assume that the infimum of the product of many of these likelihoods is lower bounded, but something that behaves like this. So it's exponential, but with order less than 1. So this zeta is something between 0 and 1. So this goes to 0 at a rate which is less than exponential of order 1. This is not the usual. Assumption. Okay, the usual assumption would be to remove the zeta here. However, to remove the zeta there means that you believe that you can have a very long sequence of time steps, and so you have your G's at the different G at each time step because it's associated to a different observation. What you're saying is you put something of order 1 there, is that you believe that there is a single point in the parameter space that minimizes each one of those likelihoods at the same time, which is unlikely. We haven't been able to yet to prove that this necessarily has to be the case for a broad class of systems, but it appears at least very likely, something very believable. Okay. And then you need an upper bound too for the likelihoods. But that's not. And this assumption is really key to the analysis. This is important. And then you, of course, need the stability of the sequences psi. So these are the predictive measures, the conditional predictive measures, and mu. So this is the posterior for the parameter. You need the stability understood as forgetting initial conditions. So, say if you have some error in your approximations at time 100, at time 100 million, you will have forgotten that error anyway. Okay. This is what the stability means in this context. If you impose these assumptions, so continuity, well, I didn't say it, but compactness of the parameter space and the state space, I have assumed compactness of the parameter space from the very beginning. Now I'm introducing compactness of the state space. This was not needed for the previous set of results, but it is needed now to have uniform convergence. Then you have a result of this sort. So you can say, you can expect, you have warranties that the LP norm of the approximation error for any time instant, so the supremum of this approximation error, will be upper bounded by a weight function that depends on n that goes to 0 with n. So you manage to provide this kind of result for the whole nested structure of particle filters. And the proof is based on the original proof from Pierre de Moral and Maurice Lyonnais from 2001. Of course, you have to feed the 2 layers in the proof. You have to take care of your parameters of how you jitter them and you keep them evolving. And again, what actually allows you to do all that is this assumption on the lower bound for the likelihood. And under these assumptions, and using the uniform convergence, one actually can prove some other things. For instance, if one takes a suitable distance between the approximation of the posterior and another measure, well, it's possible to show that the limb sup of the expected distance between the approximated posterior and a delta at some theta star, assuming that the true posteriors converge to that delta, is upper bounded by some rate function that depends on n. So this limb sup, when t goes to infinity, can also be shown to go to 0 with n, which means that we can, say, identify the parameter. Of course, this is true only for systems which are not ambiguous. So for systems where if two parameters are different, then the posteriors will also be different. And using not really the uniform convergence result, but some of the assumptions that we have made to prove it, you can also find very easily, this is almost trivial, a constant lower bound for the normalized effective sample size of your particle approximation in the parameter space. And something interesting here about the jittering again is that if you don't jitter, for instance, if you just keep recomputing the weights of your samples in the parameter space, but you don't change them, you cannot really obtain this result. So the normalized effective sample size actually goes to 0. Well, let's take a look at the actual assumptions. So what we really need. We have already been through this slide. So this is the assumption on the jittering kernel. What we are saying is that you have to take the pth order moment for your jittering kernel, and you need to have an upper bound for this that depends on n to the power of p over 2. And this has to be uniform on the support of your parameters. We have discussed this. Stability. Well, this is the same kind of stability that Pierre and Alice Guénet used in the original paper. So actually, in this slide, what I'm introducing is rather notation. Simply look at this. This capital psi of theta time t is a map that transforms one probability measure into another probability measure. To be precise, it's the map that takes the predictive measure at time t minus 1 and converts it into the predictive measure at time t. Okay. So this is the optimal update of this predictive measure, assuming that you were able to solve the involved integrals. Then this notation, psi from k to t, is the composition of all these maps from k plus 1 to time t. So in this case, k is t minus k steps, successive steps in these transformations. Now, to handle this combination of this composition of steps, one may notice that it's possible to define this transformation gamma here. It's defined recursively in this way. And this is useful to write intervals with respect to several steps in this transformation, starting from some measure alpha, as a ratio of intervals with respect to alpha. So basically, this is your initial probability measure. You transform it a number of times, and then you integrate f with respect to this transformation. So you can perform your transformation first on the function, and then integrate with respect to alpha. And then you have to normalize This one is the constant function. Well, then we can have lambda, which is essentially the same thing, but for the parameters. Here everything is simple because we don't really have the transition kind of for parameters, they are fixed. So the map is defined in an easier way. And we can still have compositions like this. Then, these are the actual stability assumptions. So what we are saying is that if we start from two different measures in the state space, alpha and beta, and we take many, in this case capital T, optimal transformations starting from these different initial conditions, eventually this error is going to vanish. Okay. So as you make this capital T be large enough, the supremum of this error is going to vanish. It's going to vanish. So the filter, in this case, the filter conditional on for any value of the parameters, the corresponding filter is going to forget the initial conditions. Okay. Yes. Oh, okay. You need a similar assumption for lambda. This is the same transformation, but in the space of the parameters. And with S1 and S2, one can already show uniform convergence. But the only thing that you have is that the limit goes to 0. If you actually want to have rates, then you have to say something about how fast these errors go to 0. So if you make them exponential first order, then you can get the rates. We said that we also need assumptions on the likelihood. We will work with two of them. This one is a standard. All we are saying is that that the likelihoods are bounded away from 0, and I'm posing that they are normalized in this case, that they have an upper bound which is 1. This is not absolutely necessary, but it makes makes analysis a bit less cumbersome, so to speak. But we could actually do without this. Using B1 alone, and this is standard, you can prove that your conditional particle filters are going to converge. But you need this other assumption, the one that I discussed earlier. So this product of the weights for the parameter samples has to be lower bounded in this manner, so by an exponential which is of order less than 1, in order to make sure that the whole algorithm, so the nested algorithm, works. You need continuity, as I said, continuity in the parameter theta, Lipschitz continuity is what you need. And if you have that, then the main theorem looks like this. So it's saying that you can have that the supremum over time of the approximation error has a bound that looks like this. So we have 3 terms. The first term is something constant, so this m is semi-integer. This q is some sufficiently large integer. This is related to the assumption on the likelihood. So, but you just take q large enough and it works. And it's easily controlled because you have the number of particles here, so you can control this term. You can make sure that this term vanishes by simply making n large. But then you have these other 2 terms which are related to the stability of the filters. This goes to 0 because of the stability of the assumption on the stability for the operator lambda, so in the parameter space. And this error comes from the errors in the approximation of the weights. If we use S4 was this one. So we say how actually these remainders go to 0. Then it's when you can obtain rates for your And so at best, at very best, this is likely to be smaller, but at very best you have n to the minus 1 over 2 plus some small epsilon. And I was going to say, for the rates you need, to obtain these rates you actually need assumption S4. But you can have this, that the limit goes to 0 without it. Moment, so I will skip the proof. The proof is roughly in the same spirit as Billmore's proof, but we mix the two layers of the particle filter, and we basically use the assumptions in the. Okay, what is important, I have already told you, is this assumption on the bounds for the likelihood. Very quickly, in 30 seconds, just a few plots, few figures. We applied the algorithm to a classical Lorentz system, so in 3 dimensions. So the system is described in this way, but we, of course, discretize it. Looks like this. And so we have 3 state variables, and we have 3 unknown parameters. We assume that we observe the state variables every 40 discrete time steps. And we observe them with an unknown scale factor. So in the end, we have to estimate 4 parameters. 3 parameters in the model plus the unknown scale factor. This is how the Lorentz system looks. And this is how the algorithm works. This is basically the error. This is averaged over a number of independent simulations, just 20 in this case. For the 4 parameters we are trying to approximate. And this straight line is what happens when you don't jitter. So your particle filter generates, you basically end up with 1 particle, and you get whatever you had at that time. Otherwise, you see how the error goes.
So the value for the non-jitter corresponds to the final point time, or something like that.
Yeah, it's basically whatever you get when your sample has impoverished.
Yeah, because but it's not a constant function of time, of course. But you just
No,
plot
it's
the
not.
last
It's
time.
not. Actually, here you don't apply. Well, yeah, you see this. Problem is that this is a pretty long time because this is continuous time. There are many time steps here.
Yeah, I don't have my glasses.
Yeah. So for some time it keeps improving. At some point it impoverishes completely.
Okay, that happens in the.
Yes. This is the same error we were looking at in the previous slide, but as a function of number of particles. And we see how it goes down, and this is an error fit. So this is a function like this. So constant times n to minus another constant. So this is the kind of form that the error bound should have, suggested by the theorem, and you see that you actually get pretty nice fit for it. This is the variance of the error. Well, that's it. I'm over time already. So just very quickly, the scheme mimics the standard particle filter, which is something that I was really interested in checking. So whether you could have something that looks like a bootstrap filter but works for the parameters as well. The algorithm is actually the same in the structure as the sequential Monte Carlo square. I started looking at this after listening to Pierre Jacob a couple of years ago presenting it. But it's strictly recursive, and you can have, under adequate assumptions, you can have convergence, even uniform convergence. I've shown some numerical illustrations, and if you want to take a look at the paper, it's posted in the archive. I hope to update it in a few days and finally submit it. That's it. Thank you very much.
Questions?
I'm surprised I didn't see anywhere explicitly the dimension of theta, because you could imagine that when you jitter at dimension d, the larger d, maybe the more or less jitter you need to have. It doesn't appear in my analysis?
Well, let me put this here. Yeah, it doesn't show up, but it doesn't show up for the same reason that it doesn't show up explicitly if you don't want to in the usual in the analysis for standard particle filters. It's hidden in the constants essentially. But
Depends what you define constant. It's not constant with respect to the dimension.
exactly. But it's
But
constantly
also your bounds clearly. I mean, your bounds in the likelihood also depend on dimensions. I mean, you assume compactness.
Yes. I'm not dealing with the dimension problem here. So here, my constants are constant with respect to the number of particles. Essentially.
As was mentioned before, one way to interpret the algorithm would be to have, like you augment your state with the parameters and then you do an numerical normalization over x. So I was wondering if you could combine that with Adam's exact approximation of parabolized filter. Maybe more interesting to you, but
Actually, yeah, I mean, there are a number of algorithms doing that nowadays, I guess, using the same kind of approximation it's the same kind of approximation that you are using in particle efficiency in constant Monte Carlo square. We have also used it in an iterative importance sampling scheme, like population Monte Carlo so far. And I mean,
in that case, would you expect that your results on the convergence here would translate to the case where you have fixed number of particles in your inner particle filters as well?
I'm sure there will be some more questions, but why don't we thank the speaker again and